Alright, so section 7.4 is on continuing with logarithms and specifically solving equations using logarithms. So that's basically the two things we want to do, is solve equations and then solve inequalities, which are pretty much done the same way. There's just a slight variation when it comes to restricting the domain. Okay, so just a kind of this interesting graphic showing the different types of tornadoes. In the last section we talked about how earthquakes use the Richter scale, and that involves logarithms. The same thing is true for tornadoes. So that shows you a little picture of, probably heard of some of these things if you live in a tornado afflicted zone like Texas or Oklahoma. F0 would be a very strong wind all the way up to F5 would be tearing homes out of the ground. F6 has never been recorded. Those would be wind speeds about 320 miles an hour. But those are also based on a logarithm scale. Anything where intensities grow by powers of 10, let's say, it would be fitting to put those on a logarithm scale, and that's called the Fujita scale, the tornado scale. Alright, so when we're solving logarithm equations, basically what we want to do is change these to exponential form. So this is the base, that's the power it's being raised to, and that's the answer. So that's the same as 36 to the 3/2 power is equal to x. And you might recall from an earlier chapter, raising something to the 3/2 power, this is the power that you raise it to, and this is the root that you're taking. Okay, an easy way to remember is the roots of a tree sink into the ground from the bottom, and the root on that fraction is the number that's on the bottom. So that's the same thing as take the square root of 36 and then raise it to the 3rd power. Always easier to take the root first and then later on cube it. The square root of 36 is 3. And 6 to the 3, that's 6 times 6 times 6 is 216. So that is what x equals right there. Okay, so the log base 36 of 216 would be 3/2 or 1.5. And you can check that in a calculator as well by plugging in exactly what you see there. You could, in a calculator, you could say the log base 36 of 216, and that would return 1.5, which is the same as 3/2. Okay, let's do a couple more here. So let's take this number here raised to that power is going to equal that answer. So 9 to the 3/2 is equal to x. That means take this root, so take the square root of 9 and then raise it to that power. Square root of 9 is 3. 3 to the 3rd is 27. So that should be our answer for x. Should be 27, and it is. Okay, right here, same idea. So let's change this to exponent form. This number raised to that power equals that answer. So 16 to the 5/2 is equal to x. This means take the square root of 16 and then raise it to the 5th power. Square root of 16 is 4, and 4 to the 5th is 1,000. I think that's 1,024 would be our x value. So x should be 1,024, and it is. Alright, this is just the idea that we've kind of talked about earlier. It basically means if you're taking the log with a certain base on one side and a log with that same base on the other, that means whatever you're taking the log of has to be equivalent on both sides. If the log base 5 of x equals the log base 5 of 8, that means x must be equal to 8. There's no other way to make those equivalent to each other. So that's called the property of equality for log functions. Most people don't have that memorized or anything. It's just the idea that's important to know. Alright, so let's apply that. So this says the log base 2 of 3x equals the log base 2 of this. So that must mean this is equivalent to this. So we can just get rid of the logs and set those equal to each other. And this is a quadratic equation, so let's put it in standard form by subtracting 3x. So we would end up with 0 equaling x squared. I'm going to put the minus 3x in the middle, and then minus 4. And you might recognize that that is something that factors. What numbers multiply to negative 4? One would be positive, one would be negative, and add to negative 3. Okay, and the only things that would work for that would be x minus 4 and x plus 1. Okay, so it's important when we solve these, we're going to get x equals 4 and we get x equals negative 1. It's important when we solve these to check both of these to make sure that we don't get something impossible. And the reason I say something would be impossible is because you can't take the logarithm of a negative number. That would be like raising a number to an exponent and getting something negative, which is impossible. So we're going to have to check both of these. We might end up getting something that's kind of extraneous here. So let's check x equals 4 into both sides of this. we get the log base 2 of 4 squared minus 4, which is the log base 2 of 12. And that's going to be equal to the log base 2 of 3 times 4, which is also equal to 12. So that one checks. Let's try x equals -1. This one actually is not going to work. So we're going to have the log base 2 of -1 squared minus 4. And that's the log base 2 of 3 times -1. And both of these are going to equal the log base 2 of -3. And you can't do that. It's impossible. If you put that in a calculator, it will return an error. Because what that base, and here's why, it's nice to understand why that's the case. Here's why that doesn't work. This is basically saying the following. It's basically saying, what number can I raise, what power can I raise 2 to get -3? And the answer is nothing. Because even if you plug in a negative number for x, plug in as big a negative number as you want, 2 to the -1000, that's the same as 1 over 2 to the positive 1000. That is still a positive number. There's no way that you can raise 2 to any power, or any number to a power, whether it's positive or negative, and come up with a negative answer. So it's important to always check your answers when you do these problems. Alright, let's do one more of those. So again, we have the same base here, and that's important. We can't take this next step unless they're the same base. The log base 3 of this equals the log base 3 of that. That means those two things that we're taking the logs of are equivalent. Do the same as what we did before by subtracting 2x. And this is now equal to 0. This would end up factoring numbers that multiply to -15, add to -2. That would be x minus 5, x plus 3. X is equal to 5. That would make this one 0. X equals -3. That makes that one 0. And if we look at this original equation, we're only going to be able to plug in 5. If you plug in -3, you're going to get the log of a negative number, which doesn't work. So that is actually a multiple choice. H doesn't appear here, but 5 is the only one that works there. -3 is extraneous. Okay, inequalities are basically done the same way. There's only one kind of exception to that, and that is when the log is less than y. You have to include this restriction. You have to include x is greater than 0. And the reason is you can't plug a negative number in here, just like we said before. That's not a problem when x is greater than y, because if something's greater than a certain number, you're not going to run into 0 to begin with. You're always going to get a positive, but we'll see what that looks like with an example. So in this one, the log is greater than 4, so we're not going to have that restriction we just talked about. In terms of how you set this up, remember that the sign right here, sometimes with inequalities you end up having to change the sign. The easy way to remember this is keep the x facing the same direction as the sign. So let's take this number raised to that power, and we'll have that answer. So 3 to the 4th, remember I want the x to be facing the same direction. Right now x is greater than, so that means x is greater than right there. And 3 to the 4th is 81. If you're not sure that we did this correctly, we can easily check it by picking any number greater than 81. And we want to do a power of 3. So 3 to the 5th power is equal to 243. So let's check that. Let's take the log base 3 of 243. Is that in fact greater than 4? Hopefully we agree that 243 meets that condition. It's greater than 81. And this number actually equals 5. So you get 5 is greater than 4. That is true. So that's a good way to check. Just pick a number bigger than 81 and plug it in, see if you get something true. Okay, let's do 3b, because 3a is very similar to what we just did. 3b, now you have x being less than. So this number, 2 raised to that power, gives us that answer. Okay. Remember that x is less than, so we have to have the same thing happening. X is less than 2 to the 4th, which means x is less than 16. There's just one more restriction. We cannot have negative numbers for x, and the reason we didn't have to do that in the other example, if x is if x is greater than 81, it's guaranteed to be positive, so we don't need to write anything else. Here x can be less than 16, but it also has to be greater than 0. Why does it have to be greater than 0? Because you can try it. Plug in a number for x right there that's not greater than 0. So in other words, a number that's less than 0, like a negative, and you'll get an error. It won't work. Okay, let's pick a number between 0 and 16 to check it. So let's try 8. So log base 2 of 8, is that in fact less than 4? That's supposed to be a question mark. this number is 3. What power do you have to raise 2 to get 8? And the answer is 3. And 3 is less than 4, so that does check out. And there's the answer right there. Okay. Same idea as what we did before with equations. Only difference would be, and that's kind of what this was saying right here. If two things have the same base, which they do, like these are both base 6, then you can just replace them with these two numbers right here, facing the same direction on the inequality sign. So this is the log base 4 of something is greater than the log base 4 of something else. That means these things must be related to each other exactly as is. This sign is facing towards or opening towards the x plus 3, so we're going to keep it opening towards the x plus 3. And now we solve this exactly like we would solve a regular equation. So we'll subtract x from both sides. 2x minus x is that. We'll subtract the 1, and we would get 2 is less than x, or x is less than 2. Okay, again, we want to be sure that we don't run into a problem with plugging negative numbers into this. Okay, so here's what that means. We don't want this to be negative or this to be negative, so let's set them both equal to 0, because 0 is the boundary line for when stuff becomes negative, and we'll see which one of these gives us more of a restriction. Oops. So this is going to give us x equals negative 3. Okay, so if we think about it, this thing, when would this thing be less than 0? Okay, actually let me alter that. We want it to be greater than 0. When would that be greater than 0? It's going to be greater than 0 as long as x is greater than negative 3. So there's our first restriction. X has to be greater than negative 3. Let's try this one right here. We get 2x equals negative 1. We divide by 2. That means x equals negative 1/2 would cause 0 to get plugged in here. Okay, again, what do we want from this? We want this thing to be greater than 0. And that thing will be greater than 0 as long as x is bigger than negative 1/2. So if you look at these two things, which one is covering both situations? Well, x could be greater than negative 3, but not greater than negative 1/2. Like negative 1 checks that one off, but it doesn't work for this one. On the other hand, if x, I shouldn't have used an x there. Let me not use x because that's going to confuse people. On the other hand, if x is greater than negative 1/2, it also covers this one right here. If x is greater than negative 1/2, it has to be greater than negative 3. So that's all we want to add. We want to add that this is greater than negative 1/2. Why are we doing that? So that we don't end up plugging in some negative number to either of those two places. Alright, so that is section 7.4. That's on solving logarithm equations and also inequalities. Hopefully it helps.